I am so excited for this. We are getting out of our review session. We've gone through the basic background stuff. It is time to start getting into the good content. Linear algebra is arriving. I am so ready for this. I just absolutely love this topic. And completely without exaggeration, let me say that when I took my first linear algebra course at the University of Michigan, once upon a time, it completely changed the way I think about everything math, physics, the world. It just gave me an entirely new conceptual framework for thinking about problems, for thinking about how we quantify different aspects of our lives, how we understand data sets, how we represent physical quantities. It's just, uh, it's mind blowing. If if you can get half as much out of this as I got out of my linear algebra learning time, it will be a huge success. All right, let's get into it. We are going to start with the basics and build up from there. So we're starting with vectors. I mentioned maybe a little bit how much I love this stuff, and I've kind of said it's useful for everything. Well, it is, but let me give a few specific examples, not just materials, but everywhere in our daily lives. But first, starting with materials, quantum mechanics is fundamentally applied linear algebra. When you really get down to it, the language of quantum mechanics is the language of linear algebra. And this is so important because this is our core toolkit for understanding materials at the atomic and molecular level. The behavior of atoms, behavior of molecules, bonding, this is all about the quantum physics of the material world at a very small scale. And without linear algebra, we simply can't do that. So it is absolutely essential for understanding materials at the lowest level. Outside of MSE, let's go to the latest, societal upheaval thing that's going on. Seems like you'll get one every other week, but whatever. Uh, AI, and by AI, I mean actual artificial intelligence, like, deep learning, applied machine learning, learning from massive data sets. All of these models are linear algebra models. When you have a large language model like, ChatGPT or whatever, it is taking human language and encoding that language as vectors and performing operations on those vectors to understand, well, understand is a loaded word, but certainly to quantify and manipulate the structure of human language to give plausible outputs given a certain input. We'll look a bit more at this after we get some more linear algebra language and toolkit because it really is a very interesting application, regardless of whether it's going to destroy the world or not. TBD on that one. It's still quite interesting. On the other side of things, weather models, believe it or not, are driven by linear algebra. When we are looking at, back to MSE for a moment, crystal structures, the symmetry language of crystallography, understanding rotations and translations in crystals, looking at symmetries, looking at space groups, these are linear algebra descriptions of the vector spaces that these crystals live in. So again, the very, very underlying fundamentals of material science are problems of linear algebra. When we are building virtual representations of the physical world. So whether this is for video games, whether this is for finite element analysis, anything in between, when we are building graphics on computers, we're doing this by, once again, say it with me, linear algebra. We are taking vectors in a modeled three-dimensional space, and these vectors represent rays of light, and they represent the surfaces and vertices of objects in that space. And by rotating and transforming these vectors, we can generate graphics, 2D graphics on a screen that represent a virtualized 3D space that will transform in the correct way, that will have the right properties of lighting and rotation and perspective and all of these things. So like it really is everywhere. There's no escaping it. Um, Even in the context of music, I might come back to this one a little bit later. But when you look at music recommendation algorithms, they're doing linear algebra. They are taking properties of music, breaking it down into different components of what kind of rhythmic structures does it have? What sort of genres does it belong to? What sort of melodic structures, duration, even, and assigning all these numerical attributes to songs, and then performing vector operations to group different songs with each other and say, hey, these things are similar. So if you like one of them, you'll probably like the others too. It's like you cannot escape from linear algebra. And these are just a few examples that I happen to pick. So that's the why it matters. It's everywhere. Okay. I'm going to stop gushing and we're just going to talk about math for a little bit. So we start with scalars. I am kind of assuming that people have seen the basic scalars and vectors stuff before in earlier math classes, physics 140, that kind of thing. But a scalar is literally a number. It is a number that does not have direction. It might be signed, it might be positive or negative, but it's not like the temperature in the room is 20 degrees left. That doesn't make sense, right? It's just 20 degrees. It is that number and nothing else. Now, in contrast with that, vectors are quantities that are intrinsically directional. That if I'm driving to work, then my velocity vector might be something like, I don't know, 60 kilometers per hour south, for example. Or if I am talking about other vector quantities, like let me think of a materials example, you have a force that's being applied to a structural component in a vehicle, for example. That force is some number of newtons applied in a certain direction, and then you get stresses that result from that applied force. Now, these kinds of vectors, these sort of magnitude and direction vectors, whether it's 1,000 newtons inward or 60 kilometers per hour south, or, pick your favorite one, this magnitude and direction concept, while it is really useful, it is actually a little bit more specific than the general concept of what a vector is. The general concept of what makes a vector is actually quite broad, very flexible. But we are going to start out with this. It's a quantity, it has a magnitude, it has a direction. We write out components of that vector, and this is an ordered list of numbers. So the ordering is important. I can't just switch around the X and Y and Z components of things arbitrarily. I have to say, this is the X part, this is the Y part, this is the Z part, and do that bookkeeping consistently. And what those components tell you is the directional content of the vector. How much in X, how much in Y, how much in Z does this total magnitude and direction thing have? And then dimensionality is just the number of components that we have. So if I have a vector with 3 components, it is a 3-dimensional object. It lives in a 3-dimensional space. So these are things that, again, I'm assuming are background for people. If there is anything here that you feel like you haven't heard before, then as always, tell me, we'll talk about it. But as I've said, the general concept is bigger than magnitude and direction and components. So as time goes on, we will expand the boundaries of the playground here. All right. For now, what are some properties of vectors that are important? So they can be multiplied, they can be added, and you can create linear combinations of them. This concept is so important, I've put it in italics. This is a big deal. So if I have a scalar times a vector, then that is a scalar multiple of that vector. This is why it's called a scalar. It scales the vector, it makes it longer or shorter, but does not change the direction. If I add 2 vectors together, possibly each one of those scaled, then I now have a combination, a linear combination of those vectors. There's a bunch of other math stuff that I'm not going to get into. It's basically common sense, reasonable things like 0 exists. And, if I do A times B plus C, then that's AB plus AC. Like that kind of thing that you would expect to be true if you don't stop and question it. Okay, here's the big new concept for today. At least I think it'll be new for most people. If you have done linear algebra before, then this will be familiar. But it's this idea of linear independence. What does it mean for vectors to be linearly independent? It means that you cannot write one of those vectors as a linear combination of the others. For example, if I look at a couple of two-dimensional vectors, so just vectors in the xy plane, then the vector 1, 0 and the vector 1, 1, those are linearly independent of each other. There's no way I can add up a bunch of 1 zeros, because that's the x direction. There's no combination of x's that gives me a y component. Those two things are independent directions. Likewise, the second vector, 1, 1, so that's pointed up and right 45 degrees. No matter how many up and right 45 degrees I do, there's no way to add all those together and get a vector that is purely horizontal. They're in different directions. Now, in 2 dimensions, usually you can just figure these things out by looking at them, and kind of picturing it or drawing it is a really good idea. But as we get to higher dimensions, it's a lot trickier to just look at things and say like, oh yes, obviously this is a linear combination of that. So what I want to do is give you a test that you can apply to test whether any given set of vectors are linearly independent or whether they are linearly dependent. So here's going to be our 3 test vectors, 1, 0, 1, 0, 1, 1, 1, 2, 3. To test whether they are linearly independent, we are going to solve some equations. They are not independent if it is possible to write one of them as a linear combination of the others. That was the definition. And so that is what's happening in this first equation is I've just taken the definition and written out as an equation. But to write that a different way, I can say that they are linearly independent if any sum of them, any linear combination of the set of vectors is only 0 when all of the coefficients are 0. So I take z, I move it to the other side, and then I have 0 equals a linear combination of my 3 vectors. And if they are linearly independent, then they can only cancel out by adding together if each of them is multiplied by 0. If they're linearly dependent, then 2 of them added together will be some multiple of the third one, and you can then get those first 2 to cancel out the third one if they are dependent. Let's look at an example. So here's my set of vectors, same ones as before, and I need to try to find the coefficients in this linear combination. Find the A and the B and the C that gives this solution of adding them up to 0. So I've written out the 3 equations in the bottom left here, my equations for A, B, and C. And I've done this just by going across the rows of the vector. So I have 1A plus 0B plus 1C equals 0. And then I have 0A plus 1B plus 2C equals 0, so on. Now we have our 3 equations written out. Here they are. I have written them with these gaps on purpose. I find it a lot easier to organize when I write things out this way. But I do have to point out an important property of this particular set of equations. So we're going all the way back to like algebra 2 here, maybe even algebra 1, which is that if you look at these 3 equations, the third equation is the sum of the first 2 equations, right? We have A plus 0 equals A, and we have 0 plus B equals B, and we have 1C plus 2C equals 3C. That means we don't actually have 3 different equations here. We only have 2 different equations. So with 2 equations and 3 variables, our system is under-constrained. This kind of remembering these properties from algebra comes up a lot when we're doing linear algebra. So remembering these rules about, oh, what if I have more variables than equations, or what if I have fewer variables than equations? That will be really useful stuff for you to review a little bit. In this case, we have 3 variables, only 2 equations. That means one of our variables is unconstrained. All right, let's work through the algebra. So these top 2 equations, I can rearrange and solve for a and b in terms of c. But then since c is a free parameter, that actually just lets us find this relationship between a and b, not a unique single solution, but rather a family of solutions. The solutions where b is half of a will solve these equations as long as a is also negative c, then we're good to go. So this means that there are infinitely many solutions to these equations. I've written a few examples here. 2, 1, negative 2 works, but any scalar multiple of that set of solutions is also a solution. This sort of, are there 0 solutions or 1 solution or finite solutions or infinite solutions? We're going to be getting more into this conceptual space as we get more into these problems of doing fancy algebra. So, what does this mean as far as the answer? It means that the 3 vectors are linearly dependent because there are values of these parameters, a, b, and c, that let you create combinations of these vectors that cancel each other out, that you can write one of the vectors as a linear combination of the other 2, and these coefficients tell you how much of each vector goes into that combination to make them equal. And if you're like, this is gross, I would say, I completely agree. Fortunately, there is a better way, and that better way is coming soon. But I wanted to show it first with language that you're already familiar with from your previous algebra classes, so that as we introduce new language, new notation, more powerful methods, you're building off of a foundation you already know. Now, I haven't actually said why linear independence matters, so let's get into that. I need to introduce a concept here. And this concept is the concept of a basis. This is really, really important in linear algebra. A span is, it's a space, and it is the space of all linear combinations of a given set of vectors. So if my vectors are, for example, going back to these nice 2-dimensional examples from earlier, then every possible combination of 1, 0 and 1, 1 makes the span of those 2 vectors. It's all of the vectors that I can find with taking these 2 vectors and adding them together in different combinations. So that's what a span is. The one that you've been using for years and years and years, maybe never thought of it in this language, is just the good old-fashioned Cartesian plane, the xy plane. We have our x unit vector, we have our y unit vector. Those things span the Cartesian plane. Every point in the plane can be written as some combination of x's and y's. So what's the idea of basis? A basis of a space is the toolkit that we use to describe that space. It's the way that we describe vectors in the space so that we can do math on them and manipulate them and solve equations. In order to be a basis of a space, there are 2 requirements. The vectors have to be linearly independent of each other, and they have to span the space. So that means that you cannot write these basis vectors in terms of each other, and it means that any other vector in the space can be built up by adding together basis vectors in the right combination. I know this is going to feel like very abstract, very theoretical, especially at first. As we work with this more, this will become more comfortable and it'll start to be meaningful. If at this point you're like, I'm not sure I get it, that's okay. This is the first round of this stuff. We'll come back to it. But what I will say from a practical point of view, I mean, math practical in the sense of being able to write and solve equations, the dream is that we want to have an orthonormal basis for our space. There are several words in here that I'll unpack more in the next few videos, but we want to be able to write down a basis for our vector space that lets us express all the vectors in that space. And we want our basis vectors to be orthogonal to each other. For now, you can just think of orthogonal as perpendicular. So, like the x axis and the y axis are perpendicular. Why are they perpendicular? Do they have to be? Well, no, actually, you can make Cartesian plane out of different axes if you want to, but it's easier when they're perpendicular because you're not mixing your coordinates together. All right. The normal part is that we want them to be unit vectors. So we want our like x and y and z basis vectors, for example, to just have a length of 1 because it's really easy to multiply 1 and it's really easy to add things that are multiplied by 1. So this is about making our lives simpler. These are not requirements to be able to do the math. They're good ideas to do the math more easily. Okay. And then just putting this out there, if you're like in a couple weeks from now, you say, you know what, linear algebra is pretty dope. I want to learn more about this. Then go look up the Gram-Schmidt orthonormalization algorithm. That's all I'm going to say about it for now. So before I wrap up this video, I was hoping to keep it under 20 minutes, didn't quite make it. I want to bring up complex numbers again. This will be a topic that pops up periodically, pun very much intended, throughout the semester. And going back to the complex plane for a second, I want to give another example of this sort of idea of basis vectors, one that maybe is a little bit more familiar to what you're used to doing math-wise, which is in the complex plane, we have a real axis and we have an imaginary axis. So in this plane, the real direction is one direction, and then the imaginary direction is a different direction perpendicular to the real direction. I'm making a big deal out of this because it actually is a big deal. It's a big deal because it means that we can describe complex numbers as vectors. We can use the language of vectors and the tools of linear algebra to do math with complex numbers. And linear algebra is an investment that really pays itself or pays for itself. You put some time into getting good at this stuff, it makes other math problems easier. That's not the reason I love it, but it really is a nice benefit. So, um, anyway, the gushing, I can't stop. I love this stuff. It's so good. Okay. But the point that I wanted to make here is that every complex number is a linear combination of ones and i's, some number of steps in the real direction plus some number of steps in the imaginary direction puts you in some place in that plane. And there's a vector pointing to that location, pointing to that number in the complex plane from the origin. How we will apply this fact, you'll see in a few days. We're going to come back to this. So that's just one more example of what a basis is. 1 and I form an orthonormal basis for the complex numbers. They're perpendicular to each other. No combination of real numbers gives you an imaginary number. I mean, no linear combination. No sum of ones and twos and threes and so on gives you an I. It's not possible. Likewise, no linear combination of i's gives you a real number. 3i plus 7i minus 20i, it's still imaginary. So these things are orthogonal to each other. They're perpendicular. They have a length of 1. 1 has a length of 1. I hope that's not a surprise. I has a length of 1 also. So that's just another example of this stuff. I think that is more than enough for right now. I need to cut this off. In the next video, we will start looking at some operations that you can do with vectors, and we'll build from there. See you soon.